Okay, here's the question for the morning. How many of you use Facebook? Anybody out there not use Facebook? And I know, like yesterday, they were kind of afraid to admit it. Yeah. Right? Yeah. There's probably some of you use it a lot. Some of you use it not as much. Right? Do some of you feel like you're like addicted to Facebook? You're on it all the time? Yeah, yeah, definitely. Or Twitter. Right? Is Twitter the new Facebook? No, nothing replaces our Facebook. Okay. Well, here's an interesting study that you may be interested in this little information. This was a study done by an education researcher at Ohio State University who says that, get this, Facebook users have lower overall grades than non-users. Okay, according to a survey of college students who also ironically said that the social networking site does not interfere with studying. Okay, she also found that user GPAs were in the 3 to 3.5 range on average compared to the 3.5 to 4.0 for non-users. Facebook users also studied anywhere from 1 to 5 hours per week compared to non-users who studied 11 to 15 or more hours per week. Actually, that's funny. She said that's why they had 4.0s. No, actually, yesterday, their first reaction was like, no, they're not telling the truth. Nobody's studying 15 hours outside of class. But, actually, and then somebody put their hand up and said, okay, wait, how are we defining studying? Right? That was an interesting question. Okay, how are we defining studying? Okay. So I know this is like, don't be prompted to now tweet this information, right? But so what's the story? Does Facebook make you get a lower GPA?
It's a correlation.
Oh, someone said it's a correlation. What do we know about correlation? We haven't gotten to the chapter yet, but what do I keep talking about anyway?
It doesn't show causation.
Correlation does not imply causation. So what could it be? What could it be? Yeah, there's a relationship here, maybe, right? But can you think of why there could be this relationship, or does it have to do with Facebook? Yeah.
Maybe people who have Facebook or use Facebook have more friends.
As somebody said to me yesterday, maybe they have a life, That aside, that's possible, but what are we looking at here? Yeah.
It could be the other way around, that people who are studying more just never got Facebook.
Oh, that's interesting. Nobody mentioned that yesterday, right? It could be that people who are not interested in Facebook are like more interested in studying more, right? It's a different direction of causality. What else? What else? Anything else you can think of? Yeah.
Could be that people get distracted by Facebook and websites.
Well, yeah.
As much.
Right. So maybe there's a third variable. Maybe it's like distractibility, right? That those people who are getting the lower grades, maybe they'd be distracted by something else just as easily, but it happens to be Facebook because that's the fad du jour, Okay? So it's just like when stuff like this comes out, so, I suppose I shouldn't be telling you this, but, when your parents look at you and say, yes, you're spending too much time on Facebook, that's why you're not doing very well in school, you can say, well, Mom, and you'll have some understanding of, yeah, there can be a relationship, but it does not imply causality. Okay? So, yeah, that's your little piece of information for today. Okay, we're going to get back now to what we were talking about, what's today, Wednesday? On Monday. For example, what's a z-score? What is a z-score? You're like, I can calculate it. I have no idea what it is. What is it? Yeah. Well, it's not one, but it is how many standard deviations, right? How many standard deviations your score is above or below the mean. That's our z-score, right? What is a standard normal distribution? Or better yet, what are the characteristics of a standard normal distribution? Yeah. Okay, he said a mean of 0, standard deviation of 1. There's also one more component. It's kind of tricky because yeah. Well, the area under the curve is 1, but this applies to, what's the thing we left out? We said center, we said spread. Shape. So what's the shape of the standard normal distribution? Normal, yeah, normal. Okay, so that's a standard normal distribution. The area under the curve is 1. And what we're going to be talking about today is how we actually find probability as area under the curve. Area under the curve. Okay? Now, before we do that, though, we're going to take a little side trip. Okay? Because we're going to be using z-scores in a different way. Okay? In psychology, let's look at psychology, often in the behavioral sciences, but let's say especially in psychology. Am I usually interested in the probability of individual scores? What am I usually interested in psychology? And I mentioned this before, but am I looking at individual scores usually? What am I looking at? Yeah. Well, probabilities of scores, but when it comes down to it, if I do a study, am I interested in one particular individual? Who am I interested in? Groups. Usually, group means, right? I'm usually interested in finding group means. And that's what we're going to be doing, is finding the probabilities of group means. So in order to do that, we have to introduce another concept, okay? First of all, imagine this. Imagine I have a population, right? I have a population, and I take a sample from that population. I get the mean of that sample, I write it down, and I throw them back into the population. I take another sample, I get the mean of that sample, throw them back into the population. I do it again, and again, and again, and again, and again, an infinite number of times. What do I have over here? What am I accruing? Are they scores? No, they're means, right? I've been writing down the means for all of those samples. So if I do that an infinite number of times, what I have is not a distribution of scores, but a distribution of means. A distribution of means, okay? That is going to be called a sampling distribution of means. A sampling distribution of means, because if I get this distribution of means, I can find the probability of means. I can find the probability of any given mean of a particular sample size if I have a probability distribution for it. Yeah? Yeah, yeah. Because we're talking theoretically here, right? We're talking theoretically. If I had this really large population and I took samples, right? It's a theoretical population. But actually, I'm going to show you an example using an actual population for you to get an idea of what's going on here. Okay? So, first of all, let's try this. Okay? Imagine I have a population, and the population is only 4 scores. Right? I can make a population as big or small as I want. This population only has 4 scores. These are the scores. Show up there? Good. Okay? 2, 4, 6, and 8. That's my population. Okay? Now, for that population, I could find the mean of that population. That's easy, right? The mean of this population. And it's mu because it's a population. Right? The mean of this population is 5. I could also find the standard deviation. What's the notation for it? Yeah, little sigma, right? Okay. So 2.24. That is the standard deviation and the mean of my population. Okay. Now, let's imagine in this population, and I put all these numbers in a hat, and I shuffle them up. And I want to draw samples from my population. How big are my samples going to be? They're going to be samples of size 2, n equals 2. Now, how am I going to do this? Well, I don't, because ultimately I'm building to a probability distribution. So what I have to do is sample this with replacement. That is, this is how it works for this little thought exercise. I take out one number and I write down the number, and I throw it back in, shuffle them up. Take out another number, write it down, throw it back in, shuffle them up. I now have these two numbers. That's my sample. I take the mean of that sample, and I write it down. And I do that procedure again, and again, and again, and again. Okay? So I'm taking samples of size 2, but I have to keep throwing them back. That's called sampling with replacement. Sampling with replacement, because if I sample without replacement, I affect the probabilities. So we don't want to do that. Yeah? I decided. I decided. It's a little thought exercise. I'm just taking samples of size 2. Okay? Now, if I want to find out what are the means, if I take samples of size 2 from my population, well, we could write it down. I'm going to show you a really easy way to do it. Okay? We create a matrix. Like this. That will show us what are the possible means that I can take for samples of size 2 from this population. Okay? So imagine first I pull out a 2, I write it down, throw it back in, and I happen to pull out another 2. What are the means? What's the mean of those two numbers? 2. What if the next time around I pull a 2 and a 4? What's going to be the mean? 3. And guess what? That's the same as if I pulled a 4 and a 2. So we can put it in there. All right? Now, what if I pull a 2 and a 6? The mean is going to be 4. That's the same as if I pulled a 4 and a 4. Or a 6 and a 2. You see the pattern that's starting to develop here? Again, all I'm doing here is trying to find the possible means. This is a simple way to do it if you have a sample of size 2. All right, 8 and 2, so the mean is going to be 5. And it's going to be 5 all the way along here. 8 and 4, the mean is going to be 6. And then 7, and then 8. Those are all the possible means that could be pulled if I'm taking samples of size 2. Okay? Now, this is essentially a distribution of means. And let's actually rewrite them. We're going to find a use for this, but let's rewrite them. Let's see. Okay, the frequency, how many times that mean occurs. Okay, now what if I wanted to find the mean of this distribution of means? Right? Because I have all these means here. It's a distribution. It is a sampling distribution of the means. Right? Sample. I took samples, so I got these distribution of means. So if I wanted to find the mean of these means, right? What would I do? What would I normally do if I wanted to find the mean of these means? It's simple. Right? How would I find it? And you're like, you're afraid this is a trick question, I know. Yeah. Yeah, I would add them all up and divide by the number of means that I had. In this case, it would be 16. That would give me the mean. But here's something really interesting. Where do I want to write this? I think I'm going to write it here. Okay. The mean of these is written like that, okay? That is because this is the mean of a sampling distribution. That x bar means you're taking not scores but means. So the mean of the sampling distribution is the same as the population mean. It's the same as the population mean, which in this case is 5. That's a nice characteristic of a sampling distribution. Okay? Now, what if I wanted to find the standard deviation of these scores? Yeah? Yeah.
So does that apply to like every single example, like in a curved way, right?
Yeah. Yeah, it's a characteristic that the mean of the sampling distribution will be equal to the mean of the population distribution. Okay? So now, if I want to find the standard deviation, what would I do? What could I do? You're thinking standard deviation, standard deviation. All I do is take my means and use them as if I would use scores. And I plug them into a standard deviation formula. And that would give me the standard deviation. However, there is a simpler relationship between this standard deviation and my population standard deviation. First of all, the standard deviation of a sampling distribution is not called the standard deviation anymore. It is called the standard error. And it's written like this: a sigma with an x bar. The standard error. So the standard error is the standard deviation of the sampling distribution of the means. Yeah? So she said, so sampling distribution means that you have a bunch of means from a sample. That's kind of simplistic, but yeah, a sampling distribution is a distribution of statistics, right? The statistic we're using here is the mean. But it's a distribution of statistics taken from a population. Yeah. We're just doing a sampling distribution of the mean, but we're going to refer to other sampling distributions as we go along. Right now, all we've talked about is one mean from one group. But yeah, life gets more complicated. We compare 2 groups, we compare 3 groups, right? There's all of that. Yeah. Sure. The standard error is the standard error, let's give the full name. The standard error of the mean is the standard deviation of the sampling distribution. Just like the standard deviation tells you approximately how far scores are from the mean, the standard error tells you approximately how far your sample mean is from your population mean. And I think I need to repeat that, right? Yeah, okay. Standard deviation tells you approximately, I don't know where I want to write this. I think I want to write it down here. The standard deviation tells you approximately how far your scores are from the mean. The standard error tells you approximately how far your sample mean is from your population mean. Yeah, can I repeat it again? Sure. Hang on just a second. And actually, what I want to do is, yeah, okay. Standard error, yeah.
Won't that always be 0 then?
What?
Because if the mean of the population, if the mean of the means
Yeah.
is always equal to the mean of the population,
Yeah.
then wouldn't the standard error be 0?
No. No, we're talking about distributions of means, right? Because, like, if I take samples, am I always going to get the same mean? No. They're going to be different means. So we're talking about, so for standard error, you're talking about approximately how far your sample mean is from your population mean. I'm not sure I'm getting to that, but maybe if I repeat it several times, I'll get it right. Yeah. What is? I need more words in the sentence.
Like, sorry.
No, it's okay. I just.
The standard error is x bar, the distance from, what's the difference between x bar and the mean of x bar?
What's the difference between x bar and the mean of x bar?
Yeah, which is with your finger.
This is a sample mean, any sample mean. This is the mean of the sampling distribution, which I think is not making you happy yet. But again, okay, let's let's imagine, let's go back to individual scores for a minute, okay? Individual scores, I have a distribution of scores, right? Any individual score, right? And this can be written, by the way, like X bar also, right? Any individual score, how far the scores are on average from the center of that distribution, that's your standard deviation, okay? But now I don't have a distribution of scores. I have a distribution of means. How far a sample mean is away from your population mean on average is your standard error. Yeah, you have to like think about this a couple times before it sinks in. Yeah. Good, good. We're not there yet. We're not there yet, but yeah, exactly. Yeah.
Now you're only taking the sample 2. What if you take the sample 3?
You know what? Those two questions go together. Hang on just a second, okay? If I don't answer it enough, we'll come back to it. So we have some concept, some vague idea of what a standard error is, yes?
Yeah.
Maybe. Okay. The standard error, instead of putting the means into a standard deviation formula, is related to the standard deviation by this. That's the formula for the standard error. Yeah, I'm not happy with the way. I'm used to having a bigger space. Let's write it again up here. Okay? The standard error is equal to my population standard deviation divided by the square root of n. That's its relationship. Much simpler than finding another standard deviation again, right? Much simpler. Yeah? No, let's actually do this. No. So what's the standard deviation for this example? You have it there. 2.24. So my question, I told you I'm going to be asking you all semester, what is n? I heard somebody say it. 2. 2. Remember? I said I was taking samples of size 2. That's why you have to be very particular about it. Samples of size 2. I was getting means from 2 scores. Hang on just a second. I do see you. Okay? Which gives us this. I haven't forgotten about your questions, but somebody over here had a question maybe applying to this. Yeah?
Yeah, I was just saying, so when you're doing standard error and calculating it, n becomes whatever sample.
N is the sample size, right? N is your number of observations in a sample. If we had chosen 3 at a time, it would have been 3. Okay? Now, let's go back to what you were asking about in terms of the size, okay? There's some very important concepts here to get. One is that standard error is smaller than my standard deviation of the population. You see that, right? It's smaller. 1.58 is smaller than 2.24. Why is that? Because means, this is an important point, means are less variable than scores. Means are less variable than scores, right? So for example, if I gave you guys an exam, there might be scores, you know, people range from, I don't know, 60 to 100. But how likely is it to get a mean of 60 or a mean of 100? It's much less likely to get a mean of 60 or a mean of 100 than it is to get individual scores of 60 or 100. So means are less variable than scores. Meaning this distribution is narrower. Okay? Yeah?
When you say less variable,
What does it mean if your things are variable? Right? If I say there's a lot of variability, what does that mean? Your scores are all over the place. Right? Your scores are all over the place. So for example, if you have a mean in a class of 85, but there's a lot of variability, the scores could be, you know, starting at 40 going up to 100. If I say there's less variability, then the scores may range from 80 to 90. Right? And again, what does this go back to? This goes back to an idea that a mean is more representative of your sample when there's less variability. A mean of 85 is much more representative of the class if your standard deviation is 2 points than it is if your standard deviation is 20 points. Y'all see that? Maybe? Okay, so that's what we mean by variability. So the means are less variable than the scores. Okay, and what we're always trying to do here is we're estimating means. We're trying to focus in on, does my sample represent my population? And how much variability tells me how much error, how much uncertainty there is about how good my mean is at estimating the population mean. Now, this goes back to your question, okay? What if I had used a sample of size 3 or 4 or 10? What happens to the standard error? If I increase n, what happens to my standard error? It decreases. It decreases. This is a very, very important little statistical concept that's going to follow you also all semester. As n increases, your standard error decreases. Yeah. Yeah. No, not the number of samples, the sample size. I decided. 4 was the population. From that population, I took a sample. How big was the sample I took? 2 numbers. Okay? No, it's okay. Yeah.
This doesn't have anything to do with you having to stick a formula for samples in degrees of freedom and stuff.
No, because right now, she just said, we're talking about how this relates to the standard deviation formulas. Right now, what you're using is the population standard deviation. We will come across a case when you use a sample standard deviation, but we're not there yet. Okay? Yeah?
So, as that increases, your error decreases
Yeah.
because n increases, you're getting closer to the size of your population.
Very good. Very good, right? If right, I increase my n, what I'm essentially doing is just getting closer and closer to the population. Right? If I have 120 students, if I take a sample of 5, so I get one number, but if I take samples of 20 or 50 or 100, I'm essentially getting closer to what the population is. And the error surrounding the mean is getting smaller and smaller. It's getting smaller and smaller. Your estimate is getting better, more precise. Yeah? You can't have a standard, well, what would be the case if you had a standard error of 0? If your standard deviation was 0. What would be a case of your standard deviation being 0? Everybody having the same score. In which case, there would be no variability. Right? There'd be no variability. So, okay? So let us go back to this for a minute, because there's a couple points I want to point out here. All right? What we were trying to do from the beginning is find a probability distribution, right? Remember what the point is. The point is I would like to find out the probability of a group mean. I'd like to find out the probabilities of means. That's what I'd like to do. So what I need to do is I need to draw the probability distributions. Now, what I want to show you first is, let's say we're going to draw a probability distribution for the population. For the population. I'm just going to do that up here. And we're going to do it very simply. For my population, what is the probability of drawing a 4? From my population of 4 numbers. 1 out of 4, right? Just 1 out of 4. What's the probability of drawing a 6? And a 2? And an 8, right? Essentially, the probabilities are the same. So that would be the probability distribution for your population. But again, what did I want to do? I wanted to find the probability distribution for my sample. You see where it's going, yeah? Okay, so let's draw it over here. All right, these are my means. Okay, let's over here, let's find our probabilities of our means. In fractions, because that'll make it simpler. What's the probability of drawing a mean of 2 from this sample of size 2? Yeah, 1 out of 16, right? Because we have a total of 16 scores. So we can just fill these in. It's the same thing. Okay? And now we'll just graph this. Sorry, this is cramped over here. Okay. So again, so what's the probability of a 2? And we can just plug this in. Yeah. Okay. Drawing a mean of 2 from this example, right? How many possible means are there? How many total means are there? 16. You only get 1, 2. So it's 1 out of 16. Yeah. You know, how many ways can you get a 4? Well, there's 3 out of 16 ways to get a 4. Okay? Notice what has happened to the shape of this distribution compared to the original probability distribution for the population. It's starting to look more normal. All right? So understand where we're going with this. I was just taking samples of size 2, and already this distribution is starting to approach a normal distribution. Why do I care? Why do I want it to be a normal distribution? Because I know the probabilities for a normal distribution. And I can find the probabilities then of my means. So and this is a really important point, as your sample size increases, the shape of your distribution starts to look more normal. Well, right now that's what we're talking about, but we're going to have other distributions where that's going to come into play. But this refers to something called the central limit theorem. The central limit theorem. And the central limit theorem essentially talks about these characteristics of a sampling distribution. So what are these major characteristics? 1, that the mean of a sampling distribution of the means will equal the population mean. That's the center. That the mean of the sampling distribution of the means will equal the population mean. That the mean of the population, the mean of the sampling distribution of the means equals the population mean. By the way, there are times when I use the word mean 5 different ways in the same sentence. Okay? So that's the center. Second component, the standard deviation, which is now called the standard error. The standard error is equal to the population standard deviation divided by the square root of n. And the third component that's really the important one in this context is that, and I'm going to say it in 2 parts here, okay? If your population distribution is normal, your sampling distribution of the means will be normal. If your population distribution is normal, your sampling distribution of the means will be normal. That's the first part. The second part, if your population distribution is not normal, the sampling distribution of the means will approach normal if your sample size is big enough. Even if your population distribution is not normal, your sampling distribution of the means will approach normal if your sample size is big enough. Now imagine your question is what? Oh, different question. Why what? No, because what you want to do is you're estimating a mean. Right? Again, remember what I do in an experiment. In an experiment, I have a group, I get a mean. But I want to use that mean to estimate what's happening in the population. How do I know if that's a good estimate of what's going on in the population? Well, I have to see, essentially, how far it is from the population mean. I have to see how much error is associated with it. Okay? That's what I'm trying to do. All right? Now, what's the question? There's a question here. I'm waiting for somebody to ask. Yeah. How big? Yeah, how big is big enough? Okay? For this class, and some people might differ a little, but for this class, 30 to 40. You need a sample size of 30 to 40 to assume that your population, your sampling distribution has become normal. How big is the population? I don't know. That's why you're taking a sample. Often you don't know how big your population is. It's not how big is the population, it's how big is your sample. Because again, see, look what happens. You know, you go from here, you're taking samples of size 2, and it's starting to get more normal. Right? Think of this. I was trying to explain this to people yesterday, and you can see it here. We can explain it with this, but I don't know if you've ever seen, there's this mechanical device, and it goes by the weird name, a quincunx. The most bizarre name. And it's essentially, you drop balls into it, and there are these pegs. And at the bottom there are bins. And a ball goes down, it goes bing, 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 and ends up in the bottom. Right? You've all seen some variation of that. Now, if you throw the balls in, do they all go evenly into all the bins on the bottom? They actually don't. What happens? They pile up in the middle, and there are fewer on the end. Why? There are more ways to get to the middle, more pathways to get to the middle than to the end. Just like here, there are more ways to get a mean of 4 or a mean of 5 than there is to get a mean of 2. So there's a higher probability of those numbers. It piles up in the middle, and it becomes more normal. As your sample size increases, that shape gets more pronounced. Yeah, back here first. That's okay, I'll go to you next. Yeah, yeah. I made it up. I just made it up. I just made it up. Why did I use 2, by the way, for this? Because I could show you this really cute little matrix, and it's easy to figure out. If you did 3, you could figure it out, but it just gets more complicated. If I did it by 3, what would happen, the major thing that would happen is the standard error would get smaller. What would change about the, well, what would change about the graphs, right? If you took a 2 and a 2 and a 2, so the mean would still be 2. But then you would take a 2, and a 4, a 2, a 4, and a 2, right? You would have all sorts of different combinations of means. So you'd have more means, right? And you'd have more possibilities. So this would start just getting even more refined. Does it make you feel better if I tell you you're never going to have to do it? No, I mean, that's a cop-out answer. But yeah, the good news for today is that you're not going to have to create your own sampling distributions. You're like, oh, she could have told us this at the beginning. What? So say again? Yeah. Okay, let me kind of tell you what the bottom line is and then kind of address your question again. The bottom line is we don't create sampling distributions. People have worked this out for us. What do I need to know about a distribution to know about the distribution? The center, the spread, and the shape. That's what we told you. It will start to be normal, right? The mean is going to be the mean of the population, and the standard deviation is going to be the standard error. We know those things. I don't always have to create a sampling distribution. This is just to show you how you get from one thing to the other. Why do we do this? Again, because I find probabilities of means. Not like we will do individual scores, but in general, I'm looking for probabilities of means. How do I do that? I have to have a probability distribution for those means. How is it created? Like this. But you're not going to have to create it. But yeah, if you had a sample size of 3, so you'd have to list all the possible ways you could get the means. Right? I take a 2, a 2, and a 2. I take a 2, a 2, and a 4. I take a 2, a 2, and a 6, a 2, a 2, and an 8. And you'd have to go through that very, very tedious process. Right? So that's why I only use 2. Okay? Now you, yeah. 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 30 to 40 observations. Observations, a sample size of 30 to 40. Okay? What else? It's all right, sort of. Okay? This is kind of the bridge between descriptive and inferential statistics. Okay? You know, we've just kind of moved from, oh, let's talk about a mean of a distribution to, I have this mean, but I want to know about a population. So what we need is this intermediary, which is a sampling distribution of the means to find our probabilities. Okay? The actual process is going to be simpler than this, but you need to understand this is the basis behind it. Okay. What else do I want to say about that? By the way, if you get down the idea of a sampling distribution, because this is, you know, ideas like this are all semester, like everything else should be easier. Let's see, is there anything else here I want to talk about? No, I don't think so. I think we did all this. Yeah, we talked about this too. Okay, now we're going to start to do examples. But now, okay, so we're stepping back now. So I've talked about how you find z-scores, right? And we talked about individual scores, and we talked about means. What we're going to go back to now is finding probabilities for individual scores. We'll find probabilities for means. We're just not there yet. We'll probably do it Monday. But so we're going to go back now to finding probabilities for individual scores. I just felt like I had to stress that so you didn't, because we do the sampling distribution, but we're not using it yet. And this is going to be quite simple. Okay? So here we go. Here's a first example. SAT scores. Assume the variable is normally distributed with a mean of 500 and a standard deviation of 100. What is the percentile rank of a person who scores 650? What are we going to do? We're going to convert it to a z-score, and then we're going to look it up on a table. So let's actually do the numbers, and then we'll look it up. I'll show you what this table looks like. Now, one thing I will recommend, not all of you have to do this, but this is a really strong recommendation. Draw a picture. Draw a picture for this stuff. And I'll warn you now, my pictures are not always to scale. But we have this normally distributed variable. What's the mean of it? 500, right? We're talking about SAT scores. Okay? What score am I interested in? I want the percentile rank for a score of 650. 650 is going to be here. I said approximately. So when I want the probability, what am I talking about? Area under the curve. Area under the curve. Which area under the curve? Anybody have any ideas? What area under the curve am I looking at here? Yeah, 650 and lower, right? Because percentile rank is the percentage of scores at or below a particular value. So I need that whole area under the curve. So the first thing we're going to do is we're going to transform this into z-scores. You don't have to do this, but sometimes what I do when I'm doing examples is I put a z-axis underneath. What's the mean of a z distribution? 0, right? And that's my z-score of 1.5. That shows you that just changing it into z-scores doesn't change its location. It's like when you change things from inches to centimeters. It doesn't change its location. It just changes the way you're expressing it. Okay? So now we have to find this area. So now we look at, in the back of your book, are these standard normal curves, or the z-tables. Okay? And I'm going to go, there's actually 3 pages of them. So I'm going to show you where this one is going to show up anyway. Unfortunately, the problem is it's really hard on these cameras to see it very well. I don't know that that's helpful. Okay? But essentially, this is what's going on. We have 3 columns here and 3 columns here on each page. What the z-table gives you is every z-score. It gives you a z-score, and then next to every z-score is 2 columns. So the areas, 2 columns for areas. This column is the area from the mean to the z-score, and this column is the area beyond the z-score. Beyond the z-score. Okay? So just by those 2 combinations of areas, you can find any area under the curve. Right? Very easy. And again, these are probabilities. All right? So how would I find the area under the curve for this example? Which columns would I use? How could I do this? Yeah? The second one and subtract it from 1. Yeah, that's a way you could do that, right? What she's saying is I could find this area. This area is the beyond z area. And I could subtract it from 1. And then I'd be left with that. Anybody else see another way of doing this, by the way? Yeah. Yeah, right? This side is 0.5, and then this is area from the mean to z. Understand something. People will see it differently. You'll have different intuitions on how to do that. That's fine. That's fine as long as you come up with the right number. What's obvious to you may not be obvious to me and vice versa. Okay? So in this example, what you do, or the way I did it, I believe, is I follow the z-scores to 1.5, right? And I did 1 minus the area beyond. So I took that area. That area, which you cannot read, is 0.0668. I'm going to write it down. That area under the curve is 0.0668. Okay? Did I answer the question? Always go back to your original questions to see whether you answered it properly. Did I answer it correctly? Yeah, right? I'm looking for the percentile rank, so what would that be? 93.32%. That's the percentile rank. All right? Now, let's take a look. We're going to do a few more examples that have slightly different things. Okay? But by the way, this is going to be the procedure all semester in some way, shape, or form. We take raw scores, we convert them, and then we find probabilities. And then we make decisions based on those probabilities. Details will change. Situations will change, but the basic idea is going to stay the same. Okay, let's do the next example. What is the percentile rank of a person who scores 433? Now it's on this side. And again, what area are we talking about? Which area are we talking about? Yeah, area under the curve, what direction though? Yeah, right? This. So I have to calculate my z-score, which is going to be negative. And you'll notice something when you go to your z-table, there are no negative values. Why are there no negative values? It's a symmetrical distribution. It's the same in the positive or the negative, so they just give you the positive values. Okay? So now I would go to a z-score of 0.67, and which column am I going to look for the area? The beyond z. That's why sometimes drawing pictures are useful, because the beyond z is going to be this tail, because it's not the mean to z. Right? So it has to be the other column. Okay? So that area and as we mentioned before, this is a percentile rank. So we answer it like that. Okay? Questions? Questions on these examples, right? This is simple so far, yeah? Yeah. Because my standard deviation is 100. It says it on the example. Right? It says normally distributed variable, mean of 500, standard deviation of 100. See it? Okay? Yeah. Where did I get the P from? The table. The table. I looked up a Z of 0.67 and I went across to the area beyond Z. Yeah. Because, right? Because it's a symmetric distribution, if you fold it in half, they're mirror images. So this is going to be the area from the mean to Z, and then this is going to be beyond the Z, which is the same as if you did it over here, right? If you folded it in half? Yeah. Yes? Okay, let's try it. Yeah.
In the first example,
Yeah.
can you explain why you use like 1 minus 0.0?
Because, and like I said, you could do it a different way, but the easiest way for me, the intuitive way for me, was I found this area, but I know that the whole area under the curve is 1. So I subtract that from 1. Yeah, did you have another question? What? About why it's that area? It gives you two options, okay? The columns give you two options. Either an area from the mean to Z, right? So if this is my z-score, either from here to here or from here to here. Those are the options it gives you. When it's a negative number, it's on this side, but it's the same idea. This is still going to be the mean to Z, right? If you fold it in half, and this is still going to be beyond the Z. That's all it is. Okay? All right, let's do another kind of question. Similar to this, but slightly different. Okay, finding the area between two z-scores. What's the proportion of the population who score between 480 and 520? 480 and 520. Sorry. All right. Into my shoulder. Huh? Okay. So what area am I looking for? All of this, right? Now, first question, how many z-scores do I have to calculate? That was interesting. It was a trick question. Do I have to calculate 2? I only have to calculate 1. Why? It's going to be the same on either side, right? It's 20 points above or 20 points below. So it's going to be positive and negative. Okay? So, actually, it's funny. When I did the calculations, I did it on the negative side. It's usually better to do it on the positive side. You'll be less likely to make mistakes. And notice something also. Like I said, I don't draw to scale very well. Really, those numbers are much closer to the middle. It's a z of 0.2, plus and minus 0.2. I just couldn't draw it because my numbers are too big. Okay? So now what? How do I find the area here? Just using the columns. Mean to z times 2. Mean to z times 2. Or, what's the kind of backward way of getting it? Anybody see it? Like I said, sometimes it's like, I have people who are like they're very nonlinear thinkers, and what's intuitive to them is like so not the way I think, but it's totally legit. Yeah. 1 minus 2 times this area. All right, another way of doing it. But okay, so I did it the simpler way. This is the area. If you go to a z of 0.2, the area from the mean to z is 0.0793. Is that the answer to the question? Is it? Why? What was the question? No. What proportion? It is the answer. Right? That's a proportion. You're done. Quizzical look? No? Okay. Yeah. 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 Proportion is always is out of 1. All right. Let's do the next question. What proportion of the population score between 350 and 450? Notice where this one is, right? This one, and again, I'm writing these numbers here because it's too cramped for me. This is this area under the curve. Between 350 and 450, it's all on one side. Here, I am going to have to find 2 z-scores. First, we find 350. Well, you could first find the other one. I don't care. And they're both negative. Okay, those are my z-scores. How am I going to find the area? Yeah. Okay, her way of doing it is saying find this area and subtract this area. Anybody see a different way? Yeah, right? You could do the mean to z for both of them and subtract them. Okay, I don't remember. What did I do here? Let's see what I did. I did the mean to z, actually, right? So I did, let's draw the picture again. To find this area, I did from here to here, and I subtracted here to here. Do you see that? And again, these numbers came from the chart, these areas. Just like a puzzle. You have 2 of the pieces, and you just need to find that 3rd piece. That's what all of these problems are like. So that should be pretty straightforward. Okay, questions on that? And then the last one I think I'm going to just briefly look at because it's kind of a mirror of something we just did. That last one here is what proportion of students score more than 433? That 433 should look a little familiar. Yeah, right? If this is 433 and this is 500, what was the area? It's the area more than. right? So we already did this. What was the z-score? Anybody remember? The z-score, minus 0.67, okay? So then the area, right, we did the percentile rank before. So all you'd have to do really is subtract it from 1. Or you could find, right, you could do it either way, either this area plus 0.5 or this area from 1, either way. Now what is that? Okay? Yeah. Mm-hmm. It gives you area beyond z and from the mean to z. Those are the two options. By the way, if you look in different books, give you different tables. This happens to be a nice table. I've seen other ones that aren't set up as well. Yeah?
So proportion just means
Means what?
just the z-score?
No. The z-score is the x value. The z-score are these values. Proportion is area under the curve. Yeah, don't confuse those, right? The z values are on the x-axis, and the proportion is the area under the curve. Actually, we're going to change the question around, which should help clarify that a little. Okay, we're going to change the question around. So up until now, what have I been doing? I've been saying, given a score, what's the area under the curve? What's the proportion? What's the probability? What's the percentage, right? That's what I've been giving you. Now, I'm going to change the question around. Look at the question. Here's a question. What score does a student need in order to score in the highest 15% of SAT scores? What have I given you here? Here I'm giving you the percent, and I want to know what the score is. So essentially, we have to work backwards. So let's draw a picture of that and see what we have to do with that. Here I've given you area under the curve. What is it and where is it on this curve? How much? .15, right? That's the area, right? It's 15%, but you have to have it in proportion terms. So it's 0.15. Where does it show up on this curve? Go back to the question and look. Yeah, right? You're saying, what that question is saying is that I'm giving you an area of 0.15. But what I want to know is, what's the score? What's the score? So that means I want to know what this value is. So in order to find that value, I have to work backwards. Now, when I go to my z-table, I'm not looking up my z-score, I'm looking up an area. What area am I looking up? Which column am I going to find this number in this 0.15? Beyond. Okay? Now, this is where it's going to get a little tricky because you can't see it as well here as I would like. What am I looking here? Okay. We're going to try to walk through this. I'll try to explain to you. Okay? I'd be looking in the area beyond z of 0.15. The problem is it doesn't give you exactly 0.15. When you're given areas, usually you can't find the exact number. What I want you to do is I want you to go to find the area that's closest. That's the rule for this type of example. That's going to change. So it's just for this type of example. I want you to find the area that is closest. So if I go down and I'm looking beyond z for 0.15, what I come across are scores that it falls between. I have an area of 0.1515. That's pretty close. But then I have an area underneath of 0.1492. 0.1492. That one's actually closer. So we go across and we see what's the z-score that corresponds to it. And it corresponds to a z-score of 1.04. So I found the area, and then I found the z-score that corresponds to it. Yeah, you're going backwards. So I know that this z-score is going to be about 1.04. But what do I want? I want my score not in z-scores. I want it in SAT terms, right? So I have to work backwards. Well, so I know that my score is going to be 1.04 standard deviations above the mean. So what is that here? We find it this way. Right? So it's 1.04 times what? Times what? 100. And what's the mean? Yeah. Yeah. I would prefer that you do it this way just because every time I've seen somebody do it that way, they made mistakes. You know, it wouldn't be wrong, and if you got the right answer, it would never be marked incorrectly. But every time I've seen somebody do it, what it meant to me, what it indicated to me was that they didn't really know what they were doing, and they tended to make mistakes. But, you know, if people can do it right, I don't care. You know? Okay, so that's working backwards. Here is where I've given you a proportion or a percentage, and I asked you to find the score. All right, let's see. We can do one more example. Area in the middle of a distribution. It's helpful for guidance purposes to be able to determine the SAT scores that cut off the lowest and highest 5% of the population. What are they? Alternatively, somebody could ask, what is the range of scores that cut off the middle 90%? This is just what we've done so far. Okay? What am I giving you here? I'm giving you an area, right? What area am I giving you? 0.05 where? Yeah, top and bottom. And I want to find the scores that correspond to that. So again, what would you do? You'd have to go to your Z table and look up what? 0.05. 0.05. And I'm going to tell you, this is one of those weird cases where it falls exactly in the middle. It falls right in the middle between z-scores of 1.64 and 1.65. On an exam or a homework, I would accept either 1.64 or 1.65, or my particular favorite, 1.645, because it falls right in the middle. But, you know. But that's only because it falls exactly in the middle. For the other ones, I'm not expecting you to interpolate. It's just because this one falls in the middle. All right? And remember here, I'm finding two scores. I'm finding two scores. So actually, right, this is the formula. It's plus and minus 1.645 times the 100 plus 500. So that I get two scores. Right, or you could write them the other way, 335 first. Sure. Let's see. Where's the best way to do it? Right about there. How's that? Yeah. You mean this less than that? If you want to. I don't, you know. Bet you could. Just make sure you get the directions right, you know. Okay? All right, questions on this? So you know, now you know probabilities for these individual scores or proportions, right? And next week we will talk about how we do it for the means. All right? Have a good rest of your week.